Here's another physics problem from chapter 19 from the OpenStack physics textbook. It gives a picture like this. It has these three capacitors, two in series that are in parallel with this third capacitor, and it says what's the equivalent capacitance. So that means what capacitor could I replace that whole thing and just have the same effect as those three right there. So if you remember, if I have capacitors in series, then this is true. 1 over C equivalent is 1 over C1 plus 1 over C2. If I have capacitors in parallel, C equivalent is C1 plus C2. So how do we deal with a situation like that here? What we need to do is to do one thing at a time. The first thing I want to do is replace two of those capacitors with just one, and then I'm going to have two again, I can do it. So in this case, I can combine these two capacitors and replace it as just one because these are in series. I can't do that over here because these are not in parallel because they do not have the same change in potential across them because of the other capacitor. These are in series because the same current would flow through them. So they're in series. So let's find the series or capacitor. We'll call this, we'll replace those with something I'm going to call C4. Okay, and then I'll redraw the picture. So 1 over C4 is 1 over C1 plus 1 over C2. You can just put this stuff in your calculator right away, but you could also get a common denominator and say 1 over C4 is C2 plus C1 over C2 C1. Right? Because if I multiply this by C2 over C2 and that by C1 over C1, they have a common denominator, C1, C2, and then I can add the top. And then I can take the inverse and I get C4 is equal to C2, C1 over C2 plus C1. Now let's go ahead and put in our values. C4 is equal to C2, which is 10. Now this is a symbol that we see a lot. This is the Greek letter mu. It's the same mu for the coefficient of friction, and it means micro. It means 10 to the negative 6. So C2 is 10 times 10 to the negative 6. So 10 times 10 to the negative 6, which is 10 to the negative 5, but I'm just writing how they wrote it. And then I have C1 is 0.3 times 10 to the negative 6. And then I have that as, I'm going to go ahead and add them because they have the same unit over here. So 10 plus 0.3 is 10.3 times 10 to the negative 6. You can do that, right? I can do stuff like that. Notice that in this case, that's farads over farads. So I get farads squared on the top divided by farads. I do get farads. The units do work. That's always a good thing to check. Okay, let's put that in our calculator. Whoa, my chalk. Draw. Okay, so I have 10 times 10 to the negative 6. I know that's 1 times 10 to the negative 5. Enter. And then I have 0.3 times 10 to the negative 6 times. And then I'm going to divide that by 10.3 times 10 to the negative 6. Divide. And I get C4 is 2.91 times 10 to the negative 7 farads. And you could write that in microfarads if you want. I don't really care. Now what we have is this. So now I have two capacitors that are in parallel. And if these two capacitors, C4 and C3, are in parallel, then C equivalent total is going to be C3 plus C4. That's not too hard, right? So C3 is 2.5 microfarads. This is actually 0.291 microfarads if I move the decimal over. So I can do this in my head. This is going to be 2.791 times 10 to the negative 6 farads, or 2.79 microfarads. If you have to use your calculator that way, that's fine, right? I don't want to use my calculator for stuff I can do in my head. It's not wrong to use your calculator. Okay, that. That wasn't too bad.